Okay. So anyway, so this is my final lecture, and I want to remind you again of the theme of the lectures and how we're going to proceed. So the first lecture I told you about this very curious property of QCD in the Regge limit, where the theory classicalizes and cross sections become unitary. And this happens at a scale much before lambda QCD. So this theory becomes strongly interacting before you reach the true fundamental infrared scale in QCD. And then I argue to you that one could write down an effective field theory that describes physics in this regime, and that was the color glass condensate. And I demonstrated to you that one can actually calculate a lot of things in this effective theory, and it matches to perturbative QCD in the appropriate limits. And then in the last lecture, I talked about the Glasma, what happens when two nuclei collide. And today I'm going to discuss thermalization. So so let me just first start out a little bit by reminding you some key aspects of the last lecture. And so that was the basic idea was the same as in the CGC, that you have a separation of scales between sources, which are large, which goes 1 over the coupling, and the fields, which are soft. Can you hear me now? Yeah? Okay. Can I let me start sharing again. Is it okay now? It should become full screen. Okay. Okay, great. Okay. So, sorry, let me start where I left off. So I was saying that you have sources and fields, and the sources, as my cursor shows, are those at large X, and they fly apart, and then the fields interact dynamically. And what I talked to you about is how to actually compute the inclusive multiplicity and higher moments of the multiplicity in principle, from writing down a theory for the fields and presence of the sources, and that was employing the Schwinger-Keldysh formalism of QCD. And so in principle, from first principles, one can actually try and compute these things. And the final result that I got for you was that the role of quantum fluctuations in the entire framework is absolutely important. So you have some classical fields that you generate, and then these classical fields, which are generated by sources, have quantum fluctuations, but these grow exponentially after the collision. So that's shown by this plot here on the right. And what they do is that they actually scramble information of the system. So they become as large as the classical fields on logarithmic timescales, so very rapidly. And then what they do is they scramble information, and that is one way to think about how the system proceeds towards thermalization. So the final result that I had for the components of the stress energy tensor, which included all the information about the evolution of weak partons in the wave function and the subsequent growth of quantum fluctuations, could be represented by this formula on the right-hand side, where you can write the result as a path integral over these large X sources, where the W's give you the distribution of color sources in the two nuclei at a given rapidity, And then in addition, for each configuration of rows of color sources, you have an additional path integral which resums all these large quantum corrections after the collision. And that's given by a spectrum of fluctuations, which is given by this F init of little a, where little a is the seed for the fluctuations, times the leading order stress energy tensor in QCD, which is given by the classical solution of the gauge field, so the Yang-Mills equations as a functional of rho 1 and rho 2, plus this little seed that one has, which is drawn from this F of A. So this path integral of multiple initializations of classical trajectories, even in one event for fixed rho 1 and rho 2, as I argued to you, can lead to something called eigenstate thermalization. And this follows the ideas of Berry, Srednicki, Rigol, and others. Okay? And it's also seen in other systems in nature. And as I mentioned, it can be understood to lead to decoherence of these strongly correlated primordial classical fields. So then I mentioned to you that one can formulate this problem in QCD, this classical statistical problem that one has, in terms of an initialization of the gauge fields at some initial time tau naught, in terms of a distribution which is stochastic. So you have these C's here, which are stochastic Gaussian random variables. The Xi's are just the plane waves of QCD gauge fields in the forward light cone. These are Hankel functions in QCD. And then the overall weight of this is given by an occupation number here, which we choose to be of order 1 over alpha s. So you have highly occupied fields, as in the Regge limit. But then you parameterize the initial distribution by some theta function, okay, where Q could be a hard scale, like the saturation scale in the problem. And you could say the shape of the distribution can be anything. In momentum space, it could be prolate or oblate, and that's controlled by this parameter psi naught, which one can vary to say whether you have an initial distribution of gauge fields, which is, you know, like a football or like an ellipse. And then you also can vary this initial occupancy, which is a number of order 1, if any which way you like, to see how the results depend on that. And so the way you do this in practice is that you're solving Hamilton's equations. So these are the classical equations of motion for QCD. So what we did in practice was SU2. It's a little simpler than SU3. We don't expect this to be qualitatively different for 3 colors as opposed to 2. It was a simulation in 3+1 dimensions, so it's a full 3+1D simulation. And one has to fix a gauge because you have redundant degrees of freedom, and we fixed a gauge which is 8 tau equal to 0. That's called the Fox-Schwinger gauge. Now it turns out that one has to also fix the additional residual gauge degrees of freedom, and like I mentioned last time, you can fix a Coulomb gauge in 2 dimensions. In 3 dimensions, to actually get the physical gluons that one, with 2 physical polarizations that one requires. So these simulations I'm going to mention are very large numerical simulations on a lattice in real time. These were 256 squared lattices in the transverse dimension and 4096 lattices in the longitudinal direction. And the reason we have such large lattices in the longitudinal direction is that you want to resolve the infrared scales that get smaller and smaller as you redshift the system due to the expansion of the plasma, of the Glasma. So you need very large lattices to resolve how the infrared scales evolve with time in this problem. So here's the result that one obtains from these 3+1D numerical simulations. And this confirms the qualitative picture that I mentioned to you. That is, so here's on the y-axis here is the gluon distribution that one extracts from these gauge fields at some given time. And that's a function of proper time tau, the transverse momentum pt, and the longitudinal wave number nu. This is very close to pz. So you can think of nu like pz in the problem. And so this is plotted as a function of nu here. So it's a rapidity wave number, which is also in pz. And then here in the other side of the axis here is transverse momentum. So there's transverse momentum on this axis, the rapidity wave number on the other axis, and on the y-axis is the number distribution. So at very early times after the collision, tau of the order of 1 over qs, all you have are these Glasma fields, which are the solution of the Yang-Mills equations of motion that I talked about last time, and they have no longitudinal momentum, so they have no pz. Okay, so the solution is boost invariant, and so because of boost invariance in wave number, it's really localized at pz equal to 0, and that's the classical solution. And if you remember, I mentioned that this classical solution gives you longitudinal pressure equal to 0. And the reason is because there are no wave modes in pz along this axis here, as you can see, right? All you have is pt modes. So the longitudinal pressure of these Glasma fields is 0. However, there are vacuum fluctuations, and these vacuum fluctuations interact with the Glasma fields. And so on a time scale, which is between 1 in units of qs and log squared, you find that these quantum fluctuations grow exponentially. Okay? And this is this Weibull instability that I mentioned to you last time, where the fluctuations grow as the exponential of the square root of time. And on a very short time scale, right, as a result, right, where tau is 1 over qs times log squared, 1 over alpha s, you get an overoccupied plasma. Okay, so pz becomes as large as pt very, very quickly due to this instability here. So the solution, which was systematic, if you remember in the Schringer-Keldysh formalism, I said you have to consider the classical equations of motion, and then you do the NLO corrections to that. It turns out that the NLO corrections become very, very large, and they give you this overoccupied system. And so this is a result of these very large-scale numerical simulation. So you can ask, okay, so this is the picture that one has. You have these highly Lorentz contracted nuclei with weak partons. You get this result of the Glasma, which is a classical solution, at a time scale 1 over qs. You have the plasma instability, which grows very rapidly. And then you get this initial overoccupation, okay, in 3 dimensions, in pt and pz. And now what happens? Because this happened very, very quickly, right? But the system can still interact and evolve. So what happens? So that's an interesting question. So it turns out that, as you can expect, there's a natural competition between the interactions of the gluons amongst each other and the longitudinal expansion, which tries to make the system anisotropic. So on the top plot, you see in momentum space, okay, a distribution in pt and pz at the initial time. Okay, say it's roughly isotropic. And then as the longitudinal expansion goes on, the system wants to redshift all the modes towards lower pz, right? Because all the higher pz particles move outwards, and so what's left in the center are just low pz particles. So that's the distribution you would get in momentum space. So the system wants to dilute. On the other hand, you have interactions among the gluons because the system is highly occupied. So the number of gluons per unit of phase space is very large. And so they are scattering off each other. Okay? So the question is, what wins? Okay, so on the one hand, the interactions want to isotropize the system by creating pz, and these, on the other hand, the longitudinal expansion wants to dilute pz by pushing everything towards lower pz. Okay? So this is the basic problem in heavy ion collisions: is, you know, what wins and how does it win, right? So someone asked me a question last time as to what happens to the pressure. And so you see that this is for different values of the oblateness or prolateness parameter of this initial distribution that I said when you do the numerical simulations. So that was this psi naught here, the oblateness parameter. So for psi naught equal to 1, you have a distribution which is pt squared plus pz squared, right? So it's isotropic. So psi naught is the measure of the anisotropy of the initial momentum distribution, and n naught, I remind you, is modulating the occupancy. So if you now go back here, you see what I plotted on the y-axis is the anisotropy of PL over PT, right? So if the system is isotropic, PL over PT equal to 1. So if you start with some initial distribution, say, which is isotropic, psi naught equal to 1, you see that the system kind of has a certain trajectory as a function of time in units of QS times the time. Okay? Now, however, if you choose very different distributions initially, you can get very different values of PL over PT initially, but then you see something remarkable, that they all start to follow the same trajectory at late times. Okay? You can do the same thing as shown in the inset with keeping psi naught fixed, right, as being isotropic, but varying the occupancy. And you see again, for different occupancies, the system at late times has the same kind of behavior. Now this behavior is very different from free streaming at late times parametrically, because if the system were truly free streaming, not interacting, then PL over PT would go as 1 over tau squared, okay? Because PZ goes as 1 over tau, and PL is proportional to PZ squared, so it would go as 1 over tau squared. So, but that's not what you see. You see that it approaches a universal tau to the minus 2/3 behavior. Okay, so the system is still interacting, but the pressure is getting smaller and smaller. Okay, but in a systematic universal fashion that seems to be independent of the initial conditions in psi naught and n naught that we formulated. In fact, one sees something truly remarkable also as a result, which is that you can show that the system becomes self-similar and approaches what's called a non-thermal fixed point. Okay? So what I mean by that is that the single particle distribution of gluons as the system evolves, which can be expressed in terms of P per PZ and T. I'm assuming that the system is homogeneous spatially in these simulations. But assume you look locally and you look at f as a function of P per PZ and PT, if you conjecture that this has some functional form of this sort here, where if the system is evolving and is self-similar, then the claim is that you can map the distributions at one given time to the distribution at a different time, which looks different, but if you do the map, then you can show that it obeys the same function at different times. Okay, so in other words, it's stationary. So it's a stationary f of s means it's stationary with some rescaling of the distribution in PT and PZ by some time with up to some powers which are given here by beta and gamma. Okay, and then there's an overall cooling parameter of the system as a function of some parameter called alpha. Okay, so the claim is that this very general distribution can be rewritten as a stationary distribution. So in principle, the distribution doesn't change as a function of time, but one has to rescale the x and x axes for these distributions by some time in P perp and PZ, and then the system has some overall cooling. Okay, now with this assumption, you see that the numerical simulations obey this beautifully. Okay, so what's shown here on the left plot are moments of this distribution as a function of PZ, right? So I take powers of PZ of this distribution and I look at different moments, right? The 0th, first, and second moment, and then you can show that if you scale the z-axis by this power t to the gamma, and then you scale the y-axis again by the same power, right, to the power n, that's a moment of this distribution, you find that the curves all sit at different times. So I take different time slices, and at each different time slice, it has exactly the same distribution after the scaling. Okay? And one can do this in looking at moments of PT as well. So these are the distributions for different times. And if I do this rescaling in terms of T of beta times P perp, you find that in the inset, all these distributions lie on top of each other. Okay? And so, remarkably, you see that the system seems to obey some similar property, That is, if I have some distribution in p perp and pz at some initial time, and then I let the system evolve, I can map the distributions at later time all to the initial distribution with this change, simple change by scaling the x and y axes by powers of t to some numbers. Okay? And then there's an overall change of normalization which goes as t to the alpha. Okay? There's an overall cooling of the system as the system evolves. So this is in principle remarkable because it suggests that one has a non-thermal fixed point in the theory. Okay? So the idea is that if you start with some highly occupied initial conditions, as shown on the left here, okay, which is very far from equilibrium, right? So because equilibrium is occupancies of order 1, this is much larger than 1. And then as the system evolves, it turns out that due to scrambling that I mentioned, there's a dual description of the system in either kinetic theory or classical statistical dynamics, the numerical classical simulations, which means that you can characterize the behavior in terms of single particle distributions, even though the system is far from equilibrium. And then what we see is that the system reaches a non-thermal fixed point. Okay? Specifically, what I mean by that is the properties are independent of the initial conditions. So if I vary psi naught and n naught, it doesn't matter. Okay, the system goes to the same behavior. So it's independent of the initial conditions. And more importantly, the system has a self-similar evolution, which is characterized by universal numbers, okay, alpha, beta, gamma, which tell you how the transverse momenta and longitudinal momenta and the overall cooling of the system change with time. Okay. Now, another fixed point that we're really familiar with of the evolution is thermal equilibrium, right? It means that at thermal equilibrium, the system becomes really static, right? The distribution doesn't change anymore. You have a thermal distribution. But this is a novel kind of a self-similar distribution where the system gets stuck in a non-thermal fixed point. So actually this is very powerful because these numerical simulations can help us distinguish between different kinetic theories that one have of how the initial conditions then evolve towards thermal equilibrium. And there are many different kinetic theory ideas that were thrown about before these numerical simulations were established. And so, for example, there was one scenario saying that you have multiple scattering in the Glasma of these overoccupied gluons, and that's what leads to thermalization. There was another set of ideas saying that these kinds of plasma instabilities play a big role even at later times, and that influences the scattering. And then there were more speculative ideas saying that you may have a transient Bose-Einstein condensate formed by soft gluons, and then this system behaves somewhat like a superfluid where you have a condensate with scattering off gluons which are harder. Okay? And so basically the logic is that anything that is not forbidden is allowed. Okay, so this is Gelman's totalitarian principle of quantum mechanics. And so there were a lot of different ideas about what was going on. So what these numerical simulations established, okay, so why, before I get there, why do we have so many different theories? And the reason has to do with the fact that when you have scattering of gluons, their colors screen by each other at the Debye scale. Okay? And so at the Debye scale, physics starts to become non-perturbative, and so it becomes more strongly correlated. And it's much harder to really know exactly what's going on in terms of what the physics of the Debye scale that's happening. So different assumptions about the Debye scale influence the dynamics. To give you a sense, for example, if you have Weibull instabilities, the Debye mass can even have an imaginary component. Okay? It can have a tachyonic mode, and that's what causes the growth of instabilities. So how one treats the Debye mass really tells you, what kind of kinetic theory that one has. So what the numerical simulations established, it picked out what the right kinetic theory is in the Glasma. Okay? So what's shown in this plot is the momentum space anisotropy. So this is the hard scale lambda sub L of PZ modes, and the divided by the hard scale lambda T of the PT modes. Okay? So that's the anisotropy parameter, which one can show is gauge invariant in this framework. And so that's what's on the y-axis. On the bottom on the x-axis, what you see is going from right to left is the decreasing occupancy with the expansion. So at the earliest times, the occupancy is 1 over alpha s, and then it's starting to decrease towards 1 as you go towards the left. Okay? So you start out the lattice simulations of these classical gauge fields with very different values of the oblateness parameter, right, of the distribution. It can be prolate or oblate. It goes from all the way from 1 to 6 here. You can also vary the occupancy by a factor of 4, the overall number there. And you see that all these different results, right, converge to one single curve, okay, as the system evolves towards increasing anisotropy. Okay, and that helps you pick between different kinetic theories. Okay? So, for example, it seems to suggest that one picture in terms of a Bose-Einstein condensate, at least one realization of that as advocated in this paper, is not followed by the numerics. Okay? Also, plasma instabilities seem to be less favored than this kind of result here, which I call BMSS, and that's this bottom-up scenario of thermalization by Bayer, Mueller, Schiff, and Son. And they actually, their result gives you the same universal parameters alpha, beta, and gamma that characterizes fixed point that I mentioned. Okay? So this is the nice feature of the numerics, is it helps pick out what is the right kinetic theory that is relevant for the subsequent evolution of the system. And so what is the interpretation of this result is that if you have such a self-similar solution, and so when you have turbulence in the system and the system evolves like a attractor solution with universal properties, so then it turns out that there's a theory of weak wave turbulence which says that if you can describe that by some effective kinetic theory, by imposing some very general boundary conditions. So one is energy conservation, the other is number conservation. In the case of QCD, we know that small angle elastic scattering is dominant. So if we assume that that is true, then you get from this very simple kinetic considerations, you get value for these numbers alpha of minus 2/3. So that's the overall cooling parameter. You get the result beta is equal to 0. That basically PT doesn't change with the evolution. And gamma equal to 1/3 is saying that PZ changes as 1 over PZ to the 1/3. Okay, so these exponents from this kind of kinetic theory are, within errors, the same exponents from the numerical simulations. Okay? And these are what appear in the bottom-up thermalization scenario of Bayer et al. So this is kind of a nice picture of this kind of turbulent dynamics, what's going on. And in fact, this says that within the Glasma, what one has at early times is a non-thermal attractor. Okay? And there's a very nice quote, which you might appreciate, which says that just like in turbulence, where you have very big eddies, they become smaller and smaller eddies, right, which feed on the velocity, so they get sort of more and more rapid. And these little worlds have smaller worlds, and so on to viscosity. So viscosity is really the microscopic scale of the fluid, and so that's kind of the picture of how turbulence works in fluid dynamics, which has been known for over 100 years, okay? Almost 200 years. So that's kind of seems to be one of the features of what one observes at early times in the Glasma. So now what? Okay, so what the bottom-up scenario. So how does this bottom-up scenario actually work? So if this is a correct kinetic theory of what's happening in the Glasma, so how does it actually work? Okay, so imagine that you have an overoccupied system of gluons which have some momentum QS and they're scattering off each other. And like I mentioned, that the scattering is dominated by small angle scattering. Okay, and at small angles you have a screening of these gluons which affects the cross section, that's a typical momentum exchange that's given by the Debye mass. So we know from kinetic theory that the scale for the Debye mass is given by the integral of the occupancy of hard gluons divided by the momentum times the coupling squared. Okay, so this is a standard Debye scaling expression that one gets from kinetic theory, which is why it's called Debye screening, right? And so now what one can show is that this feature, that there's a screening which is proportional to the number of hard modes, is actually what influences the scattering at early times. Because remember, if the system were free streaming, then PZ would just decrease as 1 over tau. Okay? But now you see that the multiple scattering of these gluons, right, generates a longitudinal momentum scale. So initially, if the particles had only some transverse momentum scale, right, which is being, and then the longitudinal momentum scale was being diluted, the multiple scattering can help build up a longitudinal momentum scale. And that's just given by a random walk, where Pz squared is the number of collisions times m Debye squared. But now you say, okay, what is the number of collisions? Okay, and so from kinetic theory, right, simple 2-to-2 kinetic theory, we know that the number of collisions per unit of time is a cross-section times the number of hard modes times 1 plus the occupancy. Now usually in dilute plasmas you would ignore this F sub h, okay? But in this case that would be a huge mistake, okay? Because F sub h is much larger than 1. So basically what controls the number of collisions is sigma nh times the occupancy, and the occupancy is given by the number of hard modes divided by the density of hard modes divided by qs squared, which is a transverse momentum, divided by pz. Okay? So basically n col contains a factor of 1 over pz, as shown here. Okay? So now if I bring pz to the left-hand side, then I get pz cubed goes as 1 over tau, okay, and that's the result that one gets. So in free streaming, pz would go as 1 over tau, okay? But because of this multiple scattering at early times, pz goes as 1 over tau to the 1/3. And this 1 over tau, this 1/3 is precisely this factor of gamma that one had in this from our numerical simulations that we saw. Okay? Our numerical simulations are really supporting this picture of multiple scattering of these overoccupied gluons, which is building up some pz, which is opposing the red shift of the system towards softer and softer modes. So, and also our simulations show that there's no late time instability as conjectured by some people, that m Debye squared at late times does not seem to show a tachyonic mode. It doesn't have an imaginary part, at least one that's visible. So this picture really suggests that you have some multiple scattering, which is a random walk, giving you this dependence on 1 over tau to the 1/3. So what happens then, right? So the occupation number, like I mentioned, goes as 1 over pz times 1 over qs squared. So this is the 1 over the momentum, right? And then it's a density which is given by qs cubed times 1 over alpha s, this is very important, times 1 over qs times tau, right? So if you now say pz goes as 1 over tau to the 1/3, right, then you can show that for time which is greater than 1 over alpha s to the 3/2, right, because this goes as 1 over tau to the 2/3. So if I bring it to the left-hand side, the occupancy is less than 1 when tau is greater than 1 over alpha s to the 3/2 times 1 over qs. So what this means is that once the occupancy becomes of order 1, the system is no longer classical. Okay, because the classical assumption always was you have very high occupancy at early times. So the moment the occupancy goes below 1, the classical simulations break down. You can't use them anymore, and one has to switch to a quantum kinetic description. Okay, but a quantum kinetic description is fine because we know kinetic theory. We know how to compute things in kinetic theory. We know how the interaction of gluons occurs in kinetic theory. In principle, one can calculate that. So the virtue of the classical simulation was that it picked out the right kinetic theory, and then from then on, one could evolve it. And the time where the classical simulations break down is given by this 1 over alpha to the 3/2 1 over QS. So in the quantum regime, something interesting happens, which is new, which is in the classical regime, even though you could have m to n kind of gluon scatterings, so you could have 2 to 2, 2 to 3, and so on, the effect of number changing processes was not very significant, okay, because you have, as many left going to right as right going to left kind of scatterings. But once the occupancy falls, right, then these 2 to 3 processes become very important, because it becomes expensive for 3 gluons to go back into 2 gluons as a function of time. It's not energetically favorable once occupancy is small. So the Bose enhancement factor works against you when you go to small occupancies. So this 2 to 3 number changing processes become very important at that point. Okay, so that's a novel feature in the quantum kinetic regime. So there's 2 steps that happen. First, you find that the soft gluons thermalize rapidly because of these number changing processes. So that you produce lots of soft gluons due to these 2 to 3 processes, and these soft gluons then thermalize relatively rapidly. Okay? And then there's a process whereby the hard gluons, which are sitting at the scale QS, they then lose their energy by being quenched by a process which is jet quenching, right? And they lose the energy to this bath of soft gluons. Okay? So just to repeat, so you have this classical regime where the occupation number is very large, right? And because of that, you can have as many n to m kind of processes going on. But once the occupancy gets to be small, less than 1, then at that point, it's energy. So then these number changing processes where you get 2 to 3 start to become very important. Now you can say, what about 2 to 4? But that's suppressed by an additional power of alpha s. Okay, so 2 to 3 is really the dominant process. And so when that happens, the 2 to 3 is dominated by the emission of soft gluons. It's Bremsstrahlung. Okay, so the soft gluons you get a lot of, and they thermalize. Okay? But then you still have the hard gluons, which radiate as soft gluons, and they're quenching. The way they lose energy to the heat bath is by a process which is like jet quenching. Okay? And this final stage of the jet quenching is identical to the jet quenching formalism that Professor Blazo must have discussed in his lectures. Okay, it's identical. So in fact, if you read the paper of Bayer et al., that discussion turns out to be identical to the later formalism that was developed with much refinements discussed by Professor Blazo. So what one gets at the end is you get a thermalized bath of gluons, of soft gluons, at a temperature which is 1 over alpha to the 5/2. This is a non-trivial calculation that gives you this times 1 over QS at a temperature which is alpha to the 2/5 times QS. So if you think about it, this is remarkable because we started out in the Regge limit with one scale in the problem and started all the way from the wave functions of the gluons, and we were able to compute from first principles in the Regge limit thermalization in terms of this one scale. Okay, we can calculate up to numbers, coefficients, the thermalization time, which is given by 1 over QS times some power of the coupling, and a thermalization temperature likewise. Okay? Now this is the thermalized bath of soft gluons. When you have this jet quenching phenomenon going on, the temperature actually goes up a little bit more. It becomes 1 over alpha to the 13/5. But that's something that's further detail of this. But the remarkable thing is that you can compute a thermalization time and the thermalization temperature. Okay? So this is, in some sense, the most important slide of these lectures, and this is something that is completely counterintuitive. Okay, and so I want you to have this as one of your takeaways: is that if you work in QCD in the Regge limit, and that's a limit of very high occupancies, alpha s goes to 0, because alpha s runs as a function of QS, and when QS becomes larger and larger, alpha s goes to 0. But like I mentioned in my first lecture, the occupancy times alpha S is a number of order 1. Okay, so it's a strongly correlated theory even when alpha S goes to 0. So a remarkable consequence is that thermalization in the Regge limit occurs almost instantaneously when alpha goes to 0. Okay? And when I say instantaneously, I mean the time scale for thermalization is much shorter than the lifetime of the system. So it can be a proton or a nucleus of size r. Irrespective of that, in the Regge limit, thermalization occurs on much faster time scales. Now, this is completely counterintuitive because your naive assumption would have been as coupling gets weak, the system should free stream. It's not interacting anymore. Okay? But the opposite happens, okay, compared to your intuition. So even though alpha is going to 0, the occupation number times alpha being equal to 1 is what controls the dynamics. And this tells you that the system is as strongly correlated as it could be in QCD. Okay, and that leads to instantaneous, almost instantaneous thermalization. So you can say, what the hell are you talking about? Okay, excuse my language. So look at this formula here, okay, that I had. So you see that tau goes as 1 over alpha to the 5/2 times 1 over QS. So as alpha goes to 0, you could tell me, oh, thermalization time explodes, right? Because it goes as 1 over alpha to some power. Can someone tell me what the flaw in that logic is? Does anyone have a guess? So because naively I'm saying that as alpha goes to 0, right, this thermalization time will go to infinity, right? But I'm claiming that that's not true. So the answer is that alpha in QCD is a function of QS, okay? And it's a log. So this formula can be written as log of QS to the 5/2 on the top divided by 1 over QS. Okay, so the log when QS goes to infinity will never beat 1 over QS. Right? So you can plot this, take log of QS to the 5/2 and divide it by QS, and you'll find that as QS becomes larger and larger, this number gets smaller and smaller. So, but the temperature, of course, gets bigger and bigger, right? So the temperature the energy density of the system grows tremendously, right? While the thermalization time decreases. It's completely consistent with that intuition. Okay, so on the one hand, you would have an intuition that if the energy density of the system locally gets bigger and bigger, you would expect that the system would, be more strongly interacting. And that intuition is completely correct, okay, because that is consistent with this picture as long as one takes into account the running of the coupling, which one has to in QCD. You cannot treat alpha as independent of QS. So you cannot take this number small while not changing this number. Because alpha is a function of QS. So if you want to change alpha, you also have to change QS. And so this goes as log of QS to the 5/2 divided by QS, and that will go to 0. Okay? So all this discussion that one may hear about, CGC versus hydro and so on is really premised upon a misunderstanding. Okay? And that misunderstanding is what I just articulated to you, because a lot of people look at this formula and say, oh, when you go to small alpha, the thermalization time is exploding. But that's actually not true. This is completely consistent with this idea. And in fact, the prediction would be that as alpha goes to 0, thermalization occurs almost instantaneously in QCD. So the big problem that we have in heavy ion collisions is really not whether thermalization is feasible or not for the smaller systems. Even for a proton at sufficiently high energies, at least locally, the system could thermalize very rapidly. The issue really is, are the saturation scales large enough for that to occur? And that's an open question that one can discuss, and so you can turn the problem around to saying, what are the saturation scales necessary for the system, or the couplings necessary for the system to actually thermalize on a rapid scale. But in the Regge limit, thermalization will occur for an arbitrarily small system almost instantaneously. So there's one takeaway from these lectures. I hope it's that one. So, Quo Vadis, thermal QGP. So what I've articulated is a description of the wave function which one can show that is far from equilibrium at early times. And then there's a memory loss due to scrambling and quantum fluctuations. And then the system flows to a non-thermal fixed point, okay, which is characteristic of turbulence in QCD. And then there's a quantum breaking that occurs where the classical dynamics is no longer valid. The occupancies become less than 1. And then there's a kinetic theory description in terms of soft radiation in Bremsstrahlung, which leads the system to thermalization and isotropization. And as Professor Blazo might have mentioned, there's a kind of quantum turbulence that occurs there due to jet quenching. And then eventually the system thermalizes. Okay? Now, I say eventually because, as I said, this actually happens very rapidly in weak coupling. The big issue is whether, what actually is a coupling for realistic energies that we have in heavy ion collisions at RIC and LHC. Now, people have taken this idea seriously, and they've actually done kinetic theory simulations. So Kurkela and his collaborators have written several papers. The first of this is shown here, the result from that. And so on the y-axis, what you have is different components of the stress energy tensor multiplied by tau to the 4/3, which is when hydro starts to become important. And on the x-axis, you have time in units of QS, and above you have time in units of Fermi. Okay? And so for a reasonable value of alpha s of 0.3, you see that on time scales of the order of 1 Fermi or so, there's a matching of this kinetic theory from bottom-up thermalization to that of viscous hydrodynamics. Okay, and so what's plotted is the transverse pressure, the energy density, and the longitudinal pressure, and you see that they kind of match onto viscous hydrodynamics on fairly reasonable time scales, assuming an extrapolation from very weak coupling to this value alpha s. Okay? And there are caveats associated with that. And one of the big caveats is the behavior of the Debye scale in very weak coupling may be qualitatively different from what it is when you increase the coupling. Okay, and that's something that is assumed to be the same, and that may actually qualitatively change these results. And so one needs to do further calculations of what this Debye scale is and how it scales with energy to understand, or temperature, to understand this better. So so this is kind of the picture that one gets, which is in bottom-up thermalization. Okay, so here's the final slide in this discussion of thermalization, and I call it from nuts to soup. Okay, so in English there's a phrase which goes from soup to nuts, which means to describe everything, but this is just a little play of words, which is saying that you have these very lumpy initial conditions from the Glasma at early times. That's this IP Glasma model, and then you have instabilities which grow, the system becomes overoccupied, you go to a non-thermal fixed point, then you have Bremsstrahlung going on, which actually in this quantum regime, which creates a soft bath, and eventually you have jet quenching of these hard gluons, which thermalizes the system, and you see that can be matched for realistic couplings onto hydrodynamics. So you have a full picture all the way from the wave function all to hydrodynamics, with the assumption that the Regge limit formulation of the CGC is the appropriate one to describe heavy ion collisions at high energies. So before I get to my last, I suggest I stop here and take questions, and then maybe we can have a 10-minute break. Okay. Okay. So thank you. Thank you, Ignazio. Um, so I, 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 I sort of went through this this framework where I talked about uh, classicalization, scrambling, and thermalization in heavy ion collisions. So if you have any questions at this point, um, please feel free to ask me. Okay, someone's raising their hand there. So I can hear you. Yes. I'm do you mind coming a little forward because there's an echo a little bit. It would help if you come to the front of the room. I hope you don't mind. Okay. Yeah. Yeah. Now it's better. So that's correct. Right. So thank you for this question. I mean, I think it's a very good question. So what? Um, what? So at the very early times when the system is formed, the occupation numbers, like I was mentioning, are very large, right? So please assume that the occupation numbers, which cause 1 over alpha s, are very large, right? So when the occupation numbers are very large, then there's no penalty for looking at m to n scatterings. Okay, so it's not just 2 to 2 scatterings that are important. You can have 2 to 3, 3 to 4. So if you think in the language of kinetic theory, there's a lot of scattering interactions of many particle initial and final states that are not suppressed when the occupancy is very large. So the language of kinetic theory becomes dangerous at the very early times. And that's why we have to do numerical simulations of the classical gauge theory. Now, as the system evolves, then you can start thinking a little bit more in terms of kinetic theory. But like as I said, it's not clear what are all the different processes that one has to take into account, right? So because you could have screenings that are different due to different reasons, they could be instabilities. All of that physics is implicitly there in what we do. So that's why what was nice was that the numerical simulations picked out what was the correct kinetic theory. A priori, we wouldn't have known which kinetic theory. They could, for example, have been a condensate created in the plasma, which then you would have to take into account, just like in a superfluid, the scattering of the condensate with the particles. So what I'm saying is that the dynamics is sufficiently many-body and complex that to know what the kinetic theory is actually required numerical simulations. Okay, but what was the very nice thing was that the system went to an attractor. It went to a turbulent attractor, which was universal. So it didn't care about the details of how the system evolved, but it went to this universal attractor solution. And attractors in general are things that we don't fully understand. Okay, and that's going to be the next part of my lecture. Because what I'm going to show you is that this result is universal to something that happens in cold atoms. even though the interactions are completely different. Okay, so all we have as guidance is these numerical simulations, but the reason that simple 2-to-2 scattering doesn't work is that the occupancies are very large, and so there's complex many-body reactions that are going on, which we are not including if you just do 2-to-2. So I hope that's at least a partial answer to your question. Feel free to follow up. So if there's something you're not happy about, that let me know. Sure. Sure. Oh yes, good. Good. Yes. Yes. Right. Yeah, so that's a very good question. So what actually happens, so you're right that initially you have just this overoccupied gluon gas, right? But then there's a process which is very similar to the Schringer mechanism where you can have pair production of quarks in the background field of these soft gluons. And it turns out that that pair production rate is very fast. So you produce a large number of quarks very rapidly, and by a time scale on the order of 1 over QS, you almost have a maximal occupancy of quarks too. Okay, so the occupancy of gluons is 1 over alpha S, and the occupancy of quarks is 1, which is kind of the max. So it would be a time scale about zero point 0.3 Fermis or so. So because QS is on the order of 1 GeV at Rick, so 1 over QS is about zero point 0.2 to zero point 0.3 Fermis or so. So it's fairly rapid. So there's an interesting paper I would recommend, which is by Alexas Mazouliaskas and Alexei Kurkela from earlier this year, or sorry, I mean last year, where they actually discuss chemical equilibration in the Glasma, and they have actually quantitative, semi-quantitative calculations which show how that evolves, and they show that chemical equilibration is reached quite rapidly due to this process. Because and I'm going to talk in the last part of my talk about Sphaleron transitions, which lead to topological fluctuations in the Glasma. And the same mechanism that controls Sphaleron transitions is also what controls quark pair production, which is quite interesting. And it's very large. So it's not a small rate. But it's sub-leading compared to the rate of gluons initially. But very quickly over time that you get a large number of quarks in the system. Now, as long as the coupling is very weak, it will continue to be sub-leading. But a reasonable question that you can ask is that as the coupling becomes large, do we have to worry about back reaction, where the quarks then influence the production of gluons? And that's a very reasonable question, but that's a quantitative question that one has to answer. If you cheat like me and you take the limit of very, very small coupling, then it's a very small back reaction. But once you increase the coupling, then a lot of physics can come in, which could change this picture that I have advocated. Okay, but that's a systematic way of changing things, right? So I always like to work in some asymptotics where I can understand things and then increase the complexity by taking more realistic values. But if I start with what I think is realistic, I may miss some things otherwise. So it's always better to start, in my philosophy, with a regime where you understand things very well and then try to extrapolate beyond, rather than say, look at what is there and then you miss some physics that may be there otherwise. Okay, so that's the philosophy that I'm following here. But you're absolutely right. Once you go to realistic couplings, there may be these issues like back reaction and so on, which may influence chemical equilibration and even thermalization. So anyway, thank you for your questions, and I can also take more questions at the end. Like to emphasize, all of what I'm talking about is in some asymptotics in the Regge limit. But like I mentioned, you get some very non-trivial results, right, in the Regge limit. So you naively have thought that because the coupling is going to zero, that thermalization would take a long time. But like I argued to you, that the thermalization actually is almost instantaneous when you go to very weak couplings. And so that's a very non-trivial result of the strongly correlated dynamics that one has. So here's another thing that I'm going to talk about, which is kind of surprising, perhaps, to you, and that's the phenomenon of universality. And I'm going to argue to you that that this is something that that is true for the hottest matter we create on Earth, which is the quark-gluon plasma, and also for the coldest matter on Earth, which are these very cold, nanokelvin, and even colder atomic gases. And so here's a picture. I once took a selfie with Wolfgang Kerele, of course, who came up with this idea and the properties of these Bose-Einstein condensates. And so what I'm going to talk about is really that the very hot matter that we're talking about is really somehow universal to these very cold atomic gases. So let's think about that. So when you think about cold atomic gases, the field theory that describes it is really that of is that of a system of self-interacting scalars. So here's the Lagrangian, or the action that I've written down with a Lagrangian of a theory of self-interacting scalars, where I have n scalar fields with denoted by the label A, which are then have a self-coupling term. So it's a phi-4 theory, okay, which is for n components of the scalar, okay? Where n can be 1 to a large number. And so now if you take this scalar theory, and then you do exactly the same thing that we did for the Glasma, you assume that it's overoccupied, that the initial distribution goes as 1 over lambda, where lambda is a coupling. Then you find the following picture for the occupancy. So on the y-axis, I plot lambda times f, where f is the occupancy, as a function of momentum, and you find this beautiful, remarkable structures in the theory. Okay, and this is actually what is obeyed by cold atomic gases. So you start with a highly overoccupied theory of cold atoms, right? And what you find is that at very large momenta, you find that there's an energy cascade in the system. So that has some universal behavior, which is p to the minus 3/2, and that's sometimes called a Kolmogorov turbulence. So there's a universal Kolmogorov turbulence where energy is transferred from the infrared to the ultraviolet, so from small momenta to large momenta, and it has a characteristic power law. Okay? And this bump here that you see is where energy is pumped into the system, either by quantum fluctuations like I described, or by some external source. Okay? And then what you find is that there's another interesting universal thing where even though energy flows to the infrared, you can have particle number flow to the ultraviolet, you can have particle number flow to the infrared. And that's described by what's sometimes called an inverse particle cascade. Okay? So this is something that's remarkable. And this inverse particle cascade leads in the far infrared to Bose-Einstein condensation. Okay? Now this Bose-Einstein condensation happens far from equilibrium. It actually is a dynamical picture of how a Bose-Einstein condensate is formed. And this also has a characteristic power law, which is given by 1 over p to the 4th. Okay? So you see this very interesting kind of structure in cold atomic gases. And now this is a cold atomic gas which is now sitting in a box. Okay, so imagine you put a cold atomic gas in a trap, and it's in a fixed box, and then you have an overoccupied system, and you let it expand, and then this is what you get. Okay, so this is a very interesting kind of feature. Now what we did was that we considered a cold atomic gas which is expanding in one dimension, just like in the quark-gluon plasma. So it's expanding just like, so on the right-hand side is shown a scalar theory with n components. So that's all, with here in this case 4 components, right? And on the left-hand side is the Yang-Mills theory. Okay? And what I plotted is the transverse momentum distribution in the two cases. And you see that in the quark-gluon plasma, which is on the left, the transverse momentum distribution goes as 1 over pt as a function of time. So it's cooling, but it has always this 1 over pt kind of behavior. While in the cold atomic gases, you see that there's a wide range in momenta where you also see this 1 over pt behavior. Okay, and in the infrared, you see a very, very different behavior which leads to Bose-Einstein condensation. But in a large inertial range of momenta, you see that the behavior goes as 1 over pt. Okay, just like in the Yang-Mills theory. Now, if you look at the longitudinal momentum distribution, you see something even more remarkable. That is, you see that you cannot tell the difference between the two theories. Okay, so I've plotted the normalized distribution with this universal exponent alpha and beta and gamma, and similarly I've plotted the longitudinal momentum here on the x-axis, which is scaled, and both the gauge theory, both the quark-gluon plasma and the cold atomic gas, this reflected by the scalar, have exactly the same momentum, universal momentum function. So this is really a remarkable and totally unexpected result that we observed, that we found that in a wide range of momenta, both scalar theories, which describe cold atomic gases, and gauge fields that describe the quark-gluon plasma, have identical scaling exponents and functions and scaling functions. So the single particle distributions can be written in this following way, where this alpha, beta, and gamma are the same for the two theories. And with regard to the question that was asked, this is very surprising from kinetic theory. Right? Suppose you try to do kinetic theory for, say gluons, right? And we know that in kinetic theory, in QCD, the scattering of gluons is dominated by small angles. For scalar theories, that's not true. For scalar theories, all angles are equally important in the scattering. So if you have two scalar fields that scatter, it's not dominated by small angle scattering. It's all angles are equally important. But then the dynamics of the two classical theories, right, when we evolve this classical statistical theories, is exactly the same. Okay, so this tells us that the usual kinetic theory picture is problematic in this. Now, in the case of the scalar theory, we see that in the deep infrared, the theory has a Bose-Einstein condensate. When we look at QCD, we see some kind of enhancement, but we can't really say that this is really a Bose-Einstein condensate. It's very hard in QCD to write down a gauge invariant parameter for something that is a Bose-Einstein condensate. So there's recent work that suggests that there might be something like this in terms of Wilson loops that one can define. And this is work by my collaborator Regge and collaborators. But there's no simple way to see that there's a Bose-Einstein condensate in the infrared. So it's possible that just like for the scalars, that in QCD there's some temporal condensate, which in some features affects the result that one has in QCD. But this is something that we don't fully understand because it's very hard to compute in kinetic theory in this regime. Now, the beauty in scalar theories is that for large n, one can actually do sophisticated 2pi 1 over n kind of calculations, as perhaps Professor Arts talked to you about. In the case of, I don't know if he mentioned that, but he's done some very nice work in that direction. And so that's something, at least in the scalar theory, one can actually do. But this universality, otherwise, is extremely surprising. And this tells us that when we think in terms of kinetic theory for the quark-gluon plasma, in the usual sense, one has to be very, very careful when you're dealing with overoccupied systems because the dynamics can be completely different. Okay? So this is kind of a remarkable kind of universality, and this is something I have to confess that we don't fully understand, okay? And because this has to do with the physics of turbulence. And so if you're someone of my age and you saw this picture of this man smoking a cigarette, everybody would know who that is, okay? But I've asked this question of younger audiences, and very few people know who this person is. So does anyone know who he is? Humphrey Bogart, that's right. So he's, so, so, so I think all the older people in the audience kind of, they define themselves by knowing who this person is, and so that's Humphrey Bogart, of course, and he's a deep thinker, and so there's, you see that with a cigarette you have these turbulent patterns, and he's trying to understand those. And there's a very nice quote by a very famous hydrodynamicist, Horace Lamb. He had a classic book on hydrodynamics. And he said, I'm an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum ultradynamics. So this tells you that he lived before quantum ultradynamics was a trivial theory now for us. But at that time, it was a very difficult theory. And he says the other is the turbulent motion of fluids. And then he goes on to say, and about the former, I am rather optimistic. And he was correct. We understand quantum ultradynamics, but I think turbulence is something that we don't really have a unified, simple theory of. It's some remarkable universal patterns that comes from nonlinear dynamics, just like we have in QCD or in scalar theories. But we don't understand why the kinetic theories of the two are the same. What is the infrared dynamics that leads them to have the same kind of description? And however, because we understand the scalar theories a little bit better in terms of these 2pi 1/n, and we don't have to worry about issues like gauge invariance in the scalar theories, then in principle one could say if there's a universality, then we could compute the properties of the quark gluon plasma in this overoccupied regime by using some features of cold atomic gases. So we could think of cold atomic gases as quantum simulators of the infrared dynamics of a quark gluon plasma in some particular features. Okay? And so this might sound a little fanciful to you, but there are actually people doing experiments now which are really, this is a really fast developing field. And so what I've shown here is actually something called a structure factor, which is a single particle distribution in a cold atomic gas. So that's cold rubidium atoms, which are in a Bose-Einstein condensate, and these are in a one-dimensional trap. Okay? And so in this simulation, in these experiments, they have not considered an expanding geometry yet. They still have trouble with that, but they're considering some static box. And so you see that, but these cold atomic gases are very highly occupied. They have occupancy which goes as 1 over the coupling, so it's far from equilibrium. So it's a very non-equilibrium system, and then you let the system expand, you release them from the trap, and then you find that, okay, you get some distribution of the structure factor, which is basically a single particle distribution, where you start with some initial distribution, which is given by this blue line here, and then the distribution changes as a function of time. So it grows as some t to the alpha, and it goes inwards as some t to the beta. Okay, so that's a distribution. And then what you find is that these different curves, if you assume that there is some scaling function of this form here, which is t to the alpha times some stationary function of t to the beta times the momentum, you find that they all lie on top of this beautiful curve. Okay, it's universal. There's a universal functional form which is given this. So on the y-axis here, you see the length scales. These are in micrometers. And then the time that's given in seconds in which this system is evolving. And you find that you get this very nice universal structure where you can extract what this alpha is and what this beta is. Now these are different from the alpha and beta that I talked about because this is not an expanding system, this is a static box. But it illustrates that one can actually now do these kinds of experiments. So in future, it may be possible that some features of strongly correlated QCD could be understood by appropriately creating the right kind of cold atomic experiment which can mimic the right features of that strongly correlated dynamics. Okay, so this is a kind of quantum simulator, an analog quantum simulator of the dynamics of strongly correlated QCD. So this is a very interesting and promising approach. And for more details, you can look at this paper here that is on the archive, but was also published in Nature. There are other groups that are also working on this stuff. Okay, so now I want to shift to something else, and this is another non-trivial feature of the Glasma, and this is something which is this remarkable chiral magnetic effect. Okay? So, as some of you may know, when you have a heavy ion collision, and you don't have really a head-on heavy ion collision, but you have a semi-central heavy ion collision, then what happens is that because there's electric charge that's being carried by the spectators, which are the spectators to this hot fluid, these charges can create extremely large magnetic fields at very short times. So these are usual ENM magnetic fields, and these magnetic fields can be as large as 10 to the 18 Gauss. Okay, so these are some of the strongest magnetic fields in nature. They are larger than those of magnetars, to the best of my understanding. So these are extremely strong magnetic fields. And so there's an interesting question at what happens to quarks and gluons in the presence of such magnetic fields, right? So now we know that only quarks can directly interact with these magnetic fields. So here's a kind of cartoon of what might happen, which could create this magnetic field. So initially, assume that the magnetic field is pointing in a certain direction, and then you have quarks, so you have up and down quarks. Now, you can have left-handed quarks, right, where the spin of the quarks is of a certain, so by left-handed, you're talking about chirality, right? And chirality is a product of spin and momentum, right? So if you, in this left-handed quarks have a spin which is given in blue and a momentum which is given in red, which are in the opposite direction, okay? While right-handed quarks have spin and momentum in the same direction. Okay, that's a definition of a right-handed quark. So similarly, you know, these up right-handed quarks have spin and momentum in the same direction, and the left-handed down quarks also have spin and momentum in the same direction. Now the down quark has a spin in a different direction from the up quark because it has a different charge, right? It's a negative charge, minus 1/3, while the up quark has charge plus 2/3. Now assume that something remarkable happens, is that the QCD vacuum, say, is more complicated, right? So the QCD vacuum has many energy degenerate vacua, which we now believe can be characterized by something called a Chern-Simons number. Okay, so it's a topological quantity which defines multiple different vacua in integer values of this Chern-Simons number, and I'm going to talk about that a little bit more as I go along. But assume that you have these multiple vacua which are labeled by integer values of a topological Chern-Simons number. Okay, so from -2 to +2. But now if the plasma is very energetic, what you can have is you can have over the barrier the quarks and gluons which live in one of these vacua have the energy to go to these other vacua. They can jump over the barrier and change their Chern-Simons number. So they can change the topological features which is characterizing the vacua that they live in. Okay, so they can go to a different vacuum, which has the same energy as the vacuum that they live in. Now, so these transitions are called so-called Sphaleron transitions, when you have over-the-barrier transitions to different vacua. And this is analogous to a mechanism for ultra-weak baryogenesis in the early universe, which explains the matter-antimatter asymmetry in the early universe. Okay, so this was first postulated in that context, but it turns out that there are also Sphaleron transitions in QCD, as I will show you in a moment. Now, what happens if there's a Sphaleron transition, right? That you change the fields in which the quarks are sitting by changing the vacuum. Okay? And something truly remarkable happens. Okay? And this goes by the name of the Atiyah-Singer index theorem. And the Atiyah-Singer index theorem tells us that the number of left-handed and right-handed quarks can change, and that difference is proportional to the amount of topological charge in the system. Okay, so if I change the topological charge, I can change left-handed quarks into right-handed quarks. And that's a remarkable feature of topology in mathematics. So the Atiyah-Singer index theorem is one of the benchmarks of topology in mathematics. And it's a truly profound feature of gauge theories. So now let's look at this blob here in the middle, right? And assume that there was a Sphalerón transition of the gluon fields that happened, okay, at that time. So what happens? Suppose I change the, I want to change left-handed quarks to right-handed quarks. So I have a topological transition of +1 topological charge. So now look at this guy here, right? I have a left-handed charge, and he wants to turn into a right-handed charge. So, but the spin of this guy is aligned along the magnetic field, and to change the spin would cost some energy, right? Because I have a S dot B in the energy, and if I change the sign of S, I would require an additional amount of energy. So the best way for it to change its chirality is to flip its momentum. Okay, so this left-handed quark flips its momentum in this direction when you have a topological transition. So the Atiyah-Singer index theorem is telling us that if you have a topological transition, you need to flip the chirality of the quarks. Okay. And so this left-handed quark wants to flip its chirality, but the way to do it is not by flipping its spin, which is in blue, right? But it's by flipping its momentum. There's no energy cost to flipping its momentum. So then it becomes a right-handed quark, right? Because now both the spin and momentum are in the same direction. So the left-handed quark became a right-handed quark. Okay? Similarly, this left-handed quark here in the middle, right, that also does not want to flip its spin. So it flips its chirality, which is given in red here. So this red guy also goes down, and that becomes this. Okay, so this left-handed quark has its spin and momentum now pointing in this, going up, while this left-handed quark, the down quark, down here, becomes a right-handed quark by flipping its momentum going downwards. So what's the result? You find that all the up quarks are flowing in the direction of the magnetic field, and all the down quarks are flowing away from the magnetic field. And what you've done is you've created a current, right? You've created an electromagnetic current in the presence of this magnetic field. And this is what's called the chiral magnetic effect. So very crucial to the chiral magnetic effect in QCD is the presence of such a topological transition. And this topological transition can only happen at early times when the magnetic field is very large, right? Because if the magnetic field is small, right, then this effect may be suppressed. Secondly, if the plasma is not deconfined, right, then you don't have free up and down quarks floating around. So then you have some much more strongly correlated dynamics going on. And so seeing such a current might be a smaller effect. Okay? So all of these things tell us that the chiral magnetic effect is a truly profound phenomenon which tells us about topology in QCD. Okay? And that's something that was really kind of a remarkable possible consequence of, there's nothing that says it cannot happen. In fact, by these arguments, it seems something that could happen. But then there's an interesting question of whether it actually does happen due to dynamics. So like I mentioned, the B fields at very early times are very large, right? And like I said, it can go up to 10 to the 18 Gauss. But then it falls very rapidly. And so the effect is likely going to come at very early times. And so people at RIC and the LHC have been looking for this effect. It's very hard find this chiral magnetic effect, and I don't have time to go into this, but let me just say that there are searches currently underway, and the STAR experiment at Regge had a dedicated run last year to search for this chiral magnetic effect, and then hopefully we are anticipating that there will be some results, either positive or negative, from this search that they will announce. Okay, so there's been an intensive study of this. Now, in the meantime, this effect has been seen in condensed matter systems. Even though in condensed matter systems, the physics does not have to do with actual topological transitions of the vacuum. It really has to do with the chiral anomaly in QED, which is somewhat simpler than this picture that one has in QCD of actual topological transitions between different vacua. So sphalerons. So this is again the picture of sphalerons that one has. So you have these multiple vacua which are characterized by some Chern-Simons number, and the physics behind it is that of the chiral anomaly in QCD. Okay? It says that the axial vector current in QCD is not conserved, and it's violated by quantum physics, which is proportional to the field strength times its dual, this Hodge dual. So this is basically E dot B in QCD. If you have a non-trivial E dot B of chromoelectric and chronomagnetic fields, then you can have a violation of the axial vector current and the isosinglet axial vector current in our case, and this can actually lead to a non-trivial chiral anomaly. And so this object here can be related to something called a Chern-Simons current, whose charge is a Chern-Simons number. Okay? And the rate of change of the Chern-Simons number is what's given by this E dot B or FF dual. So if you see a change of the Chern-Simons number with time, then that's telling you about the physics of the chiral anomaly in QCD, which is this quantum effect. Okay, and we know, as I mentioned, that you can have changes in the Chern-Simons charge due to over-the-barrier transitions in a plasma at finite energy density or temperature. And so key quantity in this is a Sphalerón transition rate. It tells you how fast you can have such Sphalerón transitions. And that's an autocorrelation function of the Chern-Simons charge or Chern-Simons number at two different times. So you look at two different times, t and t plus delta t, and you look at the standard deviation of that. So you look at the root mean squared charge of that as a function of volume and time, and then that quantity is the Sphalerón transition rate. Now we know in QCD that there is such a Sphalerón transition rate at finite temperature. So what is shown here on the top plot on the y-axis is the probability distribution of a change in the Chern-Simons number as a function of different Chern-Simons number. And you see that if you have some field configuration of hot gluons, which is given by this yellow distribution, if you cool these configurations, so what I mean by that is you take out the most energetic modes of order of the temperature, and you look at the soft infrared degrees of freedom, which is given by these blue and green histograms, you see that as a function of time, they start to line up. So that you look at different times. So you go from orange, which is at early times, to late times, and you see that they line up around integer values of this Chern-Simons charge. Okay? And then you can count the number of such transitions to different Chern-Simons charge, and you can compute the Sphalerón transition rate, and you find that this grows linearly with time. Okay, and that gives you the rate, and that goes as alpha to the fifth times t to the fourth. So in QCD, we know that there can be Sphalerón transitions at finite temperature, which can lead to due to the chiral anomaly, to the change of left-handed quarks to right-handed quarks and vice versa, depending on the topological charge. So now we can ask if there's such a thing in the Glasma, right? So imagine you have this highly occupied Glasma, which is far out of equilibrium, where the occupancy is of order 1 over g squared. So it's an occupancy which is 1 or larger. And so you start with some flat. So for simplicity, we just looked at a fixed box. So we put a highly occupied Glasma in a box, and then we let it evolve. Okay? So initially you have only one scale in the problem, that's QS. And so on the x-axis I've plotted momentum divided by QS. Since it's in a fixed box, the transverse and longitudinal momentum are the same, and that's given by P. And now I look at different times. So I start with the red plot, which is just a box initial condition, and then I let it evolve with time. And so you see that there's a change with time where the hard modes go outwards and the soft modes kind of go downwards, like here on the left of the plot. So then you see some remarkable things happen. Firstly, what you see is that with time, the system develops multiple scales. Okay, so initially you start out with just one scale in the problem, that's QS, and then you see that there's a hard scale, which is given by lambda, that gets harder and harder. That's this green curve that's going out up here to the right. And then you see that you develop a Debye scale also, which decreases with time. Okay. And finally, you also get a string tension. This is a magnetic screening scale, which also decreases with time. So what's very interesting about the Glasma is that you start with a problem which is only one scale, which is QS, and then you let it evolve, and you see that it develops all these scales, which is characteristic of a quark-gluon plasma in thermal equilibrium, right? You have a temperature, you get a Debye mass, and you get a string tension, which is a magnetic screening scale. And the string tension is something that is truly non-perturbative. It cannot be something you calculate in kinetic theory. Okay? It's a truly non-perturbative object. And the way we calculate it in the Glasma is that what you do is you compute the spatial Wilson loop. So you take, you construct a Wilson line, which is an exponential of the gauge field, and you look at the area, the integral of the area of this Wilson loop. And that can be expressed as a string tension. So it's e to the minus sigma times the area. And so then you look at the spatial Wilson loop correlator. So you look at, the trace of the spatial Wilson loop, which is trace of this Wilson line, as a function of the area, so QS squared times A, and you find that that scaling has a proportionality factor, which is a string tension. So in hot QCD, that would be the scale G squared T, which is a magnetic screening scale in the plasma. But now in the Glasma, you're starting to see all these different scales. And now you can ask whether there are topological transitions in the Glasma. And as you might have anticipated, you do see it. It's quite remarkable. So here's the probability distribution of Chern-Simons charge, right? This is a truly topological object in QCD, and that's plotted as a function on the x-axis as the Chern-Simons number. And you see that initially, at some early time, which is given by this yellow distribution, you have this noisy distribution where you cannot really tell whether there's any Chern-Simons charge. And then you start cooling the system, whereby you start taking away the harder modes, and you only look at the infrared modes at some late time, which is given by green. And you see beautifully that they line up as histograms along this integer values of Chern-Simons charge. So this is a numerical evidence for the fact that the QCD vacuum has this topological structure that I mentioned to you. Okay, and this is really quite striking, right? So we cannot calculate it analytically because the theory is fully nonlinear in that regime, right? But what we find numerically is that you actually generate this very beautiful structure, which tells us that the very soft modes in the Glasma are topological objects. Okay, they're characterized by this winding number, where which is really, so if you took a sphere which is S3 and you mapped it to the SU2 gauge group, right? There's a one-to-one mapping between different windings or mappings of the sphere to the SU2 gauge group, which is characterized by this winding number, and that's what it means in topology. To have something like this. So this is something that we're seeing, really a mathematical feature of gauge theories reflected in the actual degrees of freedom that we see in the Glasma. And what is remarkable is that this Fallon transition rate scales as a function of the string tension. So somehow it's really telling us that this topological property is a feature of truly infrared non-equilibrium dynamics, strongly interacting dynamics in the Glasma. So the Svalron transition rate divided by the string tension squared is flat as a function of time. And there's been better data since which shows that these error bars are smaller, and that's actually a pretty good illustration of this fact here. Okay, so now on the right-hand side, I've computed the Svalron transition rate as a function of time. And you find that the Svalron transition rate is quite large. It goes as QS to the fourth. But then it decreases with time, and then eventually we cannot carry this even further because you have quantum breaking the classical dynamics. The occupation number becomes smaller than 1 when you have times of alpha to the minus 7/4 for a fixed box. But we know the rate in equilibrium, so this part is something we don't fully understand. And in principle, one can construct a chiral kinetic theory to try and understand how this dynamics is going on. So there's a tremendous amount of work in the theory community to try and relate this Svalron transition rate at early times to what's happening in thermal equilibrium at late times using chiral kinetic theory. Okay, there's a big field with hundreds of papers being written on trying to understand this gap between these two dashed lines that's going on. Now this is important because in heavy ion collisions, if you really want to simulate from first principles the chiral magnetic effect, one needs to understand this whole timeline of how Svalron transitions evolve with time, right? Because it's the Svalron transitions that are creating the current, which is a chiral magnetic current. So the rate of Svalron transitions is very important to understand, and how it evolves with time is telling you the rate at which this current is developing in the quark-gluon plasma. And so this is a very interesting problem in general, and there's a lot of work going on in this field. So with regard to this question that was asked to me about quark pair production, it turns out that quark pair production in the Glasma also goes as QS to the fourth. So remarkably, the rate of the production of pairs of quarks and the flipping of the chirality of quarks, which is given by this Svalron transition rate, are the same rate. Okay, so you have this picture where you have these explosive topological configurations being created, and you can think of the quark pairs as being associated with this topological. The rate for producing these quark pairs is about the same rate as given by these topological transitions, and that's actually what's also generating a chiral magnetic current at early times. So this is a very nice picture, at least in weak coupling, that one has of the dynamics that's going on in the quark-gluon plasma. So I don't know how I'm doing with time. I think I'm pretty much at the very end. So thank you all for listening to these lectures. I hope some of these aspects of what I've discussed intrigued you. And if you have any questions, really, or comments or brickbats, feel free to contact me by email about any of the questions in these lectures, or if you want any additional references. I assume at some point the organizers will put these slides online, so you can also look at them again if you like. But thank you all for listening to these lectures. And of course, I'm happy to take questions at this point also. Very good. Here's your last chance to. Okay, great. Or maybe maybe your question will prompt them to ask questions. Yes. I mean, because let me kind of go back to the slide here. So I mean, so I mean, at late times, the only way we know how to calculate this is in thermal equilibrium. Um, so in principle, there could be something at finite barrier density, but okay, at least at finite temperature, this rate, even in thermal equilibrium, actually turns out to be extremely hard to calculate. So even though you have this functional form, which is alpha to the fifth t to the fourth, the prefactors are very hard to calculate. So Guy Moore, for example, has spent a decade or more trying to understand this deeply, and there are real subtleties because the Fallon transition rate tends to have some sensitivity to the UV in thermal equilibrium. So that's kind of makes it very hard to calculate. Paradoxically, to the best of our knowledge so far, at early times, it's somewhat easier because there doesn't seem to be any UV sensitivity. So in principle, given some initial conditions, you can actually calculate what the evolution is shown in blue here. There's a caveat, which is that the only simulations we have done are in a fixed box. So we have to consider an expanding geometry and do SU3. And so there is a problem out there for any of you students who are interested to actually do this calculation. So I think it would be a very nice calculation to do. I'm too old and lazy to do it myself, but I think there's a good. So if you want to take a look, you can look at my paper here with Zoran Schlichting and Mark Mace. And Francesco, I mean, there's another aspect, which is there's a gap here between the classical simulations and thermal equilibrium, and that really requires chiral kinetic theory. And so there's a further quantitative uncertainty which one needs to do to map the end of this dashed curve here on the left to that on the right, and that's what all these developments in chiral kinetic theory and eventually chiral magneto hydrodynamics are supposed to get, right? So I mean, right now people do some version of chiral magneto hydrodynamics with some initial conditions which are arbitrary to try and mimic the effect, right? But the parameters are uncontrolled. Okay, very good. I'd be yeah. So I'm sorry I couldn't be there in person and discuss actively with all of you. It was truly kind of has been an extraordinary time for everybody. In fact, I just found out that I got an email from my department head yesterday evening saying, Raju, our travel records tell us you're supposed to come back from Florence tomorrow. In case you do, please don't come to the lab for the next 14 days. And so I sent him an email saying, I was actually in today and I stopped by your office, but you were not there. so, so, for example, my one of our students, Farid Salazar Wong, who was at the school with you, and some of you may remember him, he actually has been put in quarantine and come to the lab for. Right, 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 right. No, yeah, so I, yeah, so y- right. So I mean, I think, yeah, I think the my concern was really not getting sick or anything, but it was really the such kind of reactions that one could get. And also now it's spreading. Sorry. I'm sorry, I didn't hear you. Oh yeah. Oh, you to be quarantined is not just a bad idea. I agree with you. Yeah, I agree with you completely. But sometimes I have to meet with students and they have PhD theses to write and so on, and sometimes you need to yell at them in person rather than over Skype. So I think it would have been a bit of an inconvenience. Right, which comes from the Italian word. That's right. It comes from yeah, right. So I think you should all be brave and all, especially you young people, will be perfectly fine. It's kind of older people like myself who may have to be a little more careful. So, but anyway, so enjoy your time in Florence. I really wish I could have been there, and I hope Francesco and friends will invite me some other time. And look forward to meeting you all in happier circumstances. So, uh, thank you very much.